This is just a quick overview of mass spring systems and how they work. So for what I'm going to tell you about, x is going to be the displacement of some mass at time t that's hanging from a spring. And maybe the idea is that maybe I push the mass in a little bit and I let it go, or maybe I pull the mass and I let it go. What I want to do is I want to just model the motion of the mass as time goes on. So x is the displacement, so how far away it is from like the equilibrium point at time t. M is like, the actual value of the mass itself. Gamma is the damping coefficient. So damping could be something like air resistance, or maybe your mass is like moving back and forth on the spring through like a fluid. Anyway, theoretically, there's some damping coefficient that goes along with whatever medium your mass is moving through. And then last, K is the spring constant. And so if you've had some physics before, K comes from Hooke's law. So what we're going to do is I'm going to tell you about how all four of these things relate to each other. So how the mass moves, which is x, it's characterized by the following second order differential equation. So m times x double prime plus gamma x prime plus kx is equal to 0. And then, of course, if you have some coordinates for like, the mass starts maybe like 1 unit away from the origin, if you've got some coordinates down, then you could talk about like finding the particular solution to like some initial value problem. But what I'm going to do is set you up for how do you solve the general solution to this thing, and maybe what does it say in terms of the three different types of systems that you might have heard that we can get before. So I've got this second order differential equation here, and our goal is maybe to solve this, right? So I want to see, if I know what the mass is, what the damping coefficient is, and what K is, then can I find what X should be theoretically? And so, in other words, that would be the solution to this differential equation. And that's what I mean too by this single differential equation characterizes what the movement of the mass is and how it depends on, again, the value of the mass itself, the damping coefficient, and the spring constant. So what we'll get into then, we'll just try to treat this as before. I know I should take this differential equation and I should look at the corresponding characteristic equation, which just change the x's to lambdas more or less. So like lambda squared now and get rid of these primes. And my idea breaks down a little bit because like this x does not become a lambda, so it should be plus k. So think about this though as being related to the following quadratic equation like we're used to. Well, maybe some other words here that I should tell you about as well. This 0 on this side, whenever it's 0 on that side, we would say that this equation is homogeneous. And in terms of mass spring systems, we would call this system free. So a homogeneous differential equation, we're going to think about that as just a free mass spring system. So that's how those two words are related to each other. Anyway, back to the stuff in pink. Here's your quadratic equation here. You want to find what the values of lambda are that make that true, so you'd use the quadratic formula, and that looks like this stuff down here. Now, what do we know? Well, we know that what lambda looks like, it really just depends on what's going on underneath this square root. Those are where my three cases are going to come from. So those three cases determine how we'll name our mass spring system. So we'll say that a system's overdamped when the stuff underneath the square root is positive, is what this says right here. And what we'll call that then, we'll call that an overdamped mass spring system, but all we're saying is that you get two distinct real roots out of the characteristic equation. So overdamped, think about that going with two distinct real roots for this characteristic equation. Similarly, we'll call a system critically damped whenever what's underneath the radical above is equal to 0. So in that case, you just get one root for lambda. You would just get minus gamma over 2m would be your only root. So what do I want you to do? I want you to relate the term for mass spring systems, overdamped. How does that relate to your diffeq? That just means you're going to get a diffeq whose characteristic equation has one repeated root. And last, we'll say that a system is underdamped whenever what's underneath the radical is negative. And if this stuff's negative then you get two complex answers. So what do I want you to do? A mass spring system is underdamped whenever the roots to the characteristic equation are complex numbers. So we're just kind of attaching some names to some concepts that you're already familiar with. You're already familiar with, again, what is the behavior, or what do these lambdas look like? I know there's three cases. So all we're really doing in this section is just attaching three more words to each of these three cases that I'm already familiar with.